After Syria fell, after Bashar al-Assad was defeated by an internal coup and then had some external help from any number of actors probably, and after the Turks took some advantage of it up in the north and the Israelis took advantage of it in the south, you may recall that I believe it was on the 20th of December, or maybe it was the 17th of December. I can't remember. Yeah, 17th of December. There was some attacks by the Israelis into Syria. And they actually, it turned out to be over 800 airstrike targets were selected that destroyed all kinds of targets in Syria, especially their air defense systems, weapons depots, arms depots, fuel depots, etc. Well, there was one particular strike that got a lot of attention at the time, and you're seeing some versions of it here on the screen because of the massive nature of the explosion. And listen, I got 2 days ago, I saw a tweet pass my desk that said that, hey, by the way, it has now been, quote, confirmed, according to this source, and they have about 400,000 followers, this Twitter account, that it was actually a test of an Israeli tactical nuclear weapon. Now, I just thought on the surface of it, it's an open secret that everybody in the world knows that Israel has nuclear weapons. That's self-evident. Everybody knows that. And given that Israel has completely took advantage of the opportunity to eviscerate what was remained of the military force in Syria, it was not at all surprising to me if they may have done that, taken advantage of the opportunity. It wouldn't have surprised me in the least. But I'm not a technical expert, and so I went to our go-to person here at Daniel Davis Deep Dive, which is MIT professor Ted Postol, because nobody's going to know more about whether it's conventional or nuclear explosions than Ted Postol, which he's proven on our show so many times. And so now then, for your benefit, we also brought him back today to try to talk about some of this. Professor, first of all, welcome back to the show.
Well, it's a great pleasure to be back and to talk about this subject.
Listen, we're always so grateful to that you take the time to not usually just answer our questions, but actually demonstrate graphically so people can really understand. I mean, the literal definition of a deep dive. So we're always really grateful for you coming on, and I know you've produced another slide deck. But first of all, let's just get the bottom line up front. Was this a tactical nuclear explosion?
No, it was definitely not a tactical nuclear explosion. I'll explain shortly why it's not. And what I decided to do is to talk a little bit, show evidence why it is not a tactical nuclear explosion, but also to try to provide information to your audience about some of the important related effects that nuclear explosions have that are absolutely different from conventional explosives. And the reason this is potentially, well, it is interesting now because we are facing the potential for an escalation to nuclear war. And my concern has been and continues to be that people do not have a real appreciation for the seriousness of what a nuclear confrontation could be. It's not that they're silly or stupid, it's just that they're not exposed to it. And nuclear weapons involve nuclear phenomena that are completely beyond the normal human experience. And frankly, if we had large numbers of nuclear weapons used, it would stay that way because most people would be dead. But I think it's very important to graphically understand in some detail the effects associated with nuclear weapons. Then it's not so abstract. So what I plan to do, assuming you guys can tolerate it and your audience can tolerate it, is to show evidence that this was not a nuclear explosion, and then expand a little on features of nuclear explosions that are completely different from what most people think they understand.
Yeah, I
And
think that's fantastic because obviously we talk about on here a lot the potential for nuclear escalation in the Russia-Ukraine war if certain actions by the West are taken. And even though we don't talk about it as much, you also have the possibility of that in the Indo-Pacific. If the U.S. ever gets involved in a war against China over Taiwan, for example, all kinds of bad things are possible. So I think it is vital to understand the true destructive power of even a limited nuclear exchange. So, yeah, first of all, if you could please explain to us why you were so conclusive and certain in your comment that this was not a nuclear explosion in Syria.
okay, well, we can do that. Why don't we just take slide 3? Oh, are you looking? Okay, that you got it. And this shows you an image, one of many, of the actual explosion. And as you'll see when I show you a nuclear explosion, you'll see no evidence for pieces of material flying out of the large area where the explosion is going on, as you see in this particular photograph. Um, uh, the reason for this is that a conventional explosion occurs much more slowly. The energy release in a conventional explosion occurs much more slowly, and the temperatures, which are very high, are not close to the temperatures generated within a nuclear detonation at various times. So, for example, um, the highest temperature you'll see in a nuclear explosion, in a conventional explosion, will be about 4,000 or 5,000 degrees Celsius. And uh, and you can see in this case, there's a lot of material in the air that's combusting, afterburning, is what it's called in the conventional explosive world, because all of the energy is not released instantly from conventional explosives. A large part of the energy is released uh, in afterburning events, which are not do not contribute significantly to the initial shock wave. If you look at this particular image, you can see evidence of a brownish cloud in the foreground. We'll see in other images I'll show you that this cloud evolves. This is probably from a secondary explosion that was set off by uh, a cascading group of primary explosions, probably bombs. Well, we know that this was an ammunition dump. That's been reported, and that's where almost all of the energy from the explosion is coming from. It's from explosions of. Oh, this is fine. This is exactly. Gary has upended me, which is good, and so we can see that this explosion is completely different in its character. Why don't we go to slide 8 in the? Here we go. Good. This is actual footage, very fast frame footage, taken of the nuclear fireball generated in the December 16, 1945 nuclear test at Trinity in New Mexico, the first nuclear weapons test. This test yielded around 25 kilotons. Uh, Today, it would be a tactical nuclear weapon, small one, small tactical nuclear weapon.
Hmm.
And what you can see is a very, very well-defined ball of light, which is almost spherical, except where it intercepts the ground. And this ball of light is 6 thousandths of a second after the detonation. So 6 thousandths of a second, 6 milliseconds, if that
Wow.
means anything. Now, the energy release occurs in stages here. So in the first few hundredths of millions of seconds, so hundredths of millions of seconds, the energy is being released by nuclear reactions inside the nuclear weapon itself. So that's in a very small volume. The volume may be a meter in diameter. So very, very high density of energy. The initial temperature inside this volume, because think of temperature as a measure of energy density. So the higher the temperature, the higher the density of energy, the concentrated volume of energy. The initial temperature is probably close to 100 million degrees Kelvin. So that's the center of the sun.
Wait a minute. 100 million degrees as opposed to, you said about 4,000 for the conventional explosion?
Yeah, right.
Wow. Okay, that's a little different.
So that tells you that things are different right there. In fact, in principle, light has a light can the reflection of light off a mirror can create what's called a photon pressure. Just the fact that the light is bouncing off the mirror. The pressure from the expanding light wave, the radiation, is higher than the pressure from expanding heated material, right, at these temperatures. In other words, don't worry about the expanding material at these temperatures. Worry about the expanding light wave in terms of, producing a force, although the energy density is so high, it doesn't matter. So what happens is this very small volume generates X-rays. If you think of a piece of metal that's been heated to a very high temperature, it looks red. It's red hot, we call it. Well, this is X-ray hot. It's just exactly the same radiation, photons, except the frequency is so high because the temperature is so high that the wavelength is basically that of X-rays. Now, it turns out that X-rays are not transparent in air. Air looks like black ink to an X-ray. So what happens is the X-rays propagate out into the air, which looks like black ink, and it creates a ball of very superheated hot air that's maybe 50 feet, tens of feet in size. So it's still very small, but it's superheated to maybe 1,000,000 degrees Kelvin. So we've gone from 100 million degrees to 1,000,000 degrees. The temperature at the center of the sun is about 20 million degrees. So, there's still a lot going on at 1,000,000 degrees Kelvin. And if you actually look at the density of air inside this small ball of superheated atmosphere, the density of air is very close to the same as the density of air in the atmosphere. That's because all of the energy is propagated out at the speed of light, and the air has not had a chance to even move, even though it wants to expand because it's obviously so high temperature, and the pressure is millions, hundreds, tens of millions, hundreds of millions of pounds per square inch, but it hasn't had a chance to move. Well, it then starts to expand at about 1,000,000 miles per hour, and it's acting like a very fast-moving piston on the surrounding air. And
by the way, what size of a blast are you describing right now? How many kilotons?
I'm surprised, 10 kiloton blast.
Well, that's relatively small, so it can get a lot bigger.
Well, the region of superheated area would be larger. For example, if you had a 1 megaton blast, instead of being a few tens of feet in diameter, it would be maybe 200 or 300 feet in diameter. So the area of superheated mass would be tremendously larger for a higher yield weapon.
But the temperatures themselves would be similar?
Very close. Yeah, very close to the same. Because the energy densities are similar, but within confined to a smaller volume, which means when they expand into a fireball of maximum size, they expand into a fireball of smaller size if the yield is lower.
Got it.
Than with a much higher yield weapon. Now, the maximum size of the fireball is going to continue to expand for 1/10 of a second in this case. This is 6,000ths of a second. So 1/10 of a second is going to be hundreds of milliseconds. So a tenth of a second would be about 100 milliseconds. So we're seeing this at very early time. And the temperature of this air in this fireball at this time is very high. I can only guess, but maybe 100,000 degrees Kelvin, maybe something on that order. Could be 50,000, could be 120,000, but it's very, very hot. Not a million degrees anymore. It's cooling, rapidly expanding. It's acting like a fast-moving piston on the surrounding air, which doesn't yet know that it's about to be hit by this wall of expanding bubble. Now, if you look at the ground below, at the very bottom of this ball, you see it's the ground is luminous ahead of the expanding fireball front. Now, what's going on there is you have pieces of dirt in the ground, rock, whatever.
Yeah.
And so much light and heat is coming in at such a high rate that the surface of a grain of sand gets enormously hot relative to the rest of the grain of sand, let's say with a flame, the grain of sand would tend to heat up uniformly, but the thermal conduction is finite, and so much light and heat comes in that the surface of the heat of the sand becomes superheated, and just it's brittle, so it explodes. It explodes like an explosive material, and in the process of exploding, it shatters the rest of the piece of sand, which in turn gets exposed to this tremendous amount of light from the fireball. All of this stuff is being thrown into the atmosphere, thrown into the air near the ground. This is very efficiently heating the air to an extremely high temperature, and the shock wave near the ground is just creeping ahead of the shock wave at higher altitudes, because the air is so hot that it's propagating more quickly in this superheated air relative to the air being compressed by the expanding
so
shock.
That's 0.006 of a second. How does this evolve? What are the
Well, as we go to the next slide, we have an explanation of what we're about to see. In the middle of this particular diagram, you see a cartoon of the fireball. In this particular diagram, the fireball is a bubble in the air. It's literally expanded to its maximum size in the diagram, which means in this case it's maybe 200 meters in diameter for this particular weapon. The density of air inside the fireball is about 1% that of the atmosphere. So it's a bubble in the air. It's a vacuum, weak vacuum in the air. The temperature at this point is probably radiating at a temperature of about 4,000 or 5,000 degrees Kelvin. It's cooled a lot. At its peak, when the fireball reached its maximum size of 200 meters, it was radiating light and heat at a rate comparable to 10,000 degrees Kelvin. Now, the surface of the sun is 6,000 degrees Kelvin. So the area of this little ball, which is 100, maybe 150 meters in diameter, the surface area of this ball is radiating light and heat at about 10 or 15 times higher than the equivalent surface of the sun, except of course it's near the ground. It's not 90 million miles away.
Right.
It's hundreds of meters away. So I'm going to talk about the effects of the fireball. And so most people focus on the blast wave, which I'll talk very briefly about here. But most of my discussion is going to be on the heat and light generated by this fireball, which is tremendous. So this larger circle you see on the top of the diagram is the shock wave that is generated by the initial expansion of the fireball. The fireball acts like a fast-moving piston on the surrounding air as it rushes outward at a speed much greater than the speed of sound, and it creates a compressed shell of air. We'll see evidence for that in the photographs I next show you. And but this primary shock, in this case, reaches the ground, and you get a secondary shock generated by reflection of the primary shock off the ground. And so this second circle, which looks, which is traveling behind the first circle, is the ground shock. So if you've seen depictions of the Enola Gay experience, there've been some films about it. You see when they're running away after they drop the bomb and the bomb detonates, they first get hit with a shock wave, shakes the plane, and then there's a second shock wave that shakes the plane. And that is the shock that reflected off the ground.
Wow, I never knew that. That's interesting.
Yeah, so if you go see a depiction of this, where they try to do a good job explaining it, you see the aircraft shakes, and then there's a second shaking, which is nearly as intense as the first shaking. So on the ground, though, what you have is, you see at the ground, there is a point where the primary and secondary shock coalesce. And so the primary shock in this particular diagram is about 3 pounds per square inch at this point in the detonation. And so is the secondary shock. It's very close to the same pressure. But the area where the shocks coalesce are 6 pounds per square. It's the addition of the two shock waves.
Yeah.
So what was done in all targeting exercise, what we do in all targeting exercises is we adjust the height of burst so we get a maximum overpressure at a desired range. It's not the same for all desired maximum overpressures, but in Hiroshima, the altitude of burst was about 1,600 feet for the 12 kiloton weapon. So the reason for that was you want this mock front to form, giving you a higher overpressure on the ground to a greater range, so you can do more blast damage. In the next slide, we can actually see what's actually happening. In this particular slide, we see the fireball. We notice that there's some spots on the fireball. What that is when the nuclear weapon detonates, it of course vaporizes all the material in the nuclear weapon, which is heavy material. It's uranium or plutonium, it's steel, there's of course aluminum and other things, but mostly heavy materials. And these materials get accelerated outward at fantastic speeds, but the speed is lower than the speed at which the fireball is expanding. But as the fireball gets bigger and cools, it slows up in its expansion. And what happens is this material catches up and just splashes up against the edge of the fireball, because the edge of the fireball is very dense, because it's compressing a shell of air, which we can't see in this photograph. We'll see in the next photograph the shell of air that is compressing. And so it just splashes up against the dense air that is the shell of compressed atmosphere. If you look at this belt that's at the bottom of the fireball, that's the mock front forming, where the secondary and the primary shock are coalescing. And of course, you see all this dust on the ground, which is being kicked up. And that what happens there is this reflected shock, it slaps the ground at a very intense overpressure, and the ground kind of goes outward, and the speed of sound in ground is higher than the speed of sound in air, so it's kicking up dust as the shock wave propagates through the ground ahead of the shock wave in the air. Now notice that the altitude of that dust cloud is tens of meters in this particular case. It's going to be hundreds of meters in the case of a bigger nuclear explosion. That dust is going to create an environment on the ground where people in the target area can't see anything. In other words, if you were in the area and you happened to survive the blast wave as it passed over, which would be unlikely, but you couldn't see what's around you. You just have nothing but dust.
Really almost like what happened after the Twin Towers fell on 9/11.
Exactly.
Enormous dust cloud, but much larger, you're saying.
But much more intense. And you literally would not be able to see. It would be like being in a sandstorm in terms of what you can see. It wouldn't be a sandstorm has high winds as well. There would be high winds associated with the blast wave when it went by, but then it would just be sitting. You'd have all this dust in the air, and it would be there for quite a while, minutes, critical minutes in the case of. So if we go to the next, I'm sorry.
Okay. No, okay. Well, after you go to the next slide, I wonder if the next you can, because you've mentioned light several times, and I know elsewhere in your presentation you talk about the damaging effects of the light, worse than what people may think. I wonder if you could talk about that.
I want to. Yeah, I'll. Yeah. So if we go to slide number, let's go to slide number 11. If can you count that high, Gary?
Oh man.
I'm tracking with you.
You're running out of figures.
Tracking with you. Here's 11 right here. Here's 11.
It's too hard for Gary. He's on top of it.
Thanks a lot, Gary. So this is 53 milliseconds, 53 thousandths of a second. Remember what we saw earlier was 6 thousandths of a second. And you can see that the fireball is cooled considerably. So the brightness of the fireball is lower, and because of that, you can see this ring of brightness that's ahead of the expanding fireball, which is the compressed air shock, which itself is very high temperature and itself is luminous. Was not visible in the earlier photograph because the brightness from the fireball was well beyond the dynamic range of the camera to be able to see the relatively dim but very bright compressed shock. And here again, notice that the walls of the fireball, as you look down toward the area to the ground, are near vertical. That is the Mach front where the primary and secondary shock are coalescing. So if we jump to slide 13, this is 9 seconds later. So this is 9,000 milliseconds. And you can see the dust cloud rising. We have a length scale there. So in the next slide, what I show is the original fireball at 6 thousandths of a second. So you can see it's much smaller.
Wow.
And in the next slide, we see the fireball at around 50 thousandths of a second. So you can see the fireball is getting very near its maximum size at 50 thousandths of a second. It will reach its maximum size at 100 thousandths of a second, 100 milliseconds. And but it will do so very slowly now because it's the pressure inside the fireball is dropping rapidly. And you can see that the maximum size of the fireball is very close to the diameter of the stem from the exploding nuclear weapon. Now, if we go to slide 18, we have an example, which is not too impressive to the untrained eye, of a piece of slate from a slate roof that was at Hiroshima, relatively near the explosion. What you have when you have sheetrock on a roof is I have a sheetrock, and then I place underneath the sheetrock another piece of sheetrock, so the water will come off the sheetrock and fall onto the sheetrock below, and then I place another sheet below. So each piece of sheetrock is partially covered by some sheetrock above it. So when you go to this photograph, what you're seeing is the difference in the surface between, if we go back to the slide, Gary, there we go, thank you. You see the area that was illuminated below it is pocked. It's got tiny holes in it. Now, what happened there is the light from the fireball came in at such a high rate that the top of the sheetrock just exploded from thermal expansion, sudden thermal expansion, superheating of the surface. Now, experiments were done on this sheetrock afterwards to determine the temperature of the sheetrock for a very short period of time when the fireball was brightest. And that temperature was about 4,000 degrees Kelvin. So that's as hot as, very close to the temperature of an exploding conventional weapon. Now, if we go to slide 19, the next slide, we can see evidence of how the fireball does damage. This looks like a shadow. Well, it is a shadow. This shadow was created by the valve stem, which happened to be in between the wall behind it and the light from the fireball. And the light area you're seeing in this particular photograph is not light from an illumination source. What you're seeing is the paint on the metal surface that's been blistered by the light of the fireball. So this is permanently burnt into the surface of the light of the fireball. Did a lot of damage to that surface. If we go to the next slide, we see further evidence. This occurred at about 4.5 kilometers from the explosion in Nagasaki, which was a higher yield explosion.
4 kilometers.
And you can see there was a man who cast a shadow. He was obviously exposed to the fireball. I'll show you what that means very shortly. And of course, he had a ladder there. You can see evidence for the ladder. And there was something hanging on the wall, probably some strap of some kind. And those intercepted the light of the fireball, protecting the surface below. But of course, the painted surface was damaged by the flash from the fireball. In the next slide, we see a very clear example of how the light from the fireball gets absorbed and reflected by different surfaces. In this case, this is a piece of material. It was obviously dark stripes on a light background. And you can see areas where the dark area of the material absorbed the heat, the light and heat from the fireball. It's just like you wear white on a bright day, so it reflects the sunlight off you. In this case, if you wear black, it's much hotter. The shirt would absorb the light. In this case, the black material absorbed the light. It was so much light that it burst into flames or melted. And the white material reflected enough of the light that it did not reach a high temperature where it either melted or burst into flames. Of course, if it were closer, everything would have burnt up. If it was further away, the material might look like the material that you see that was uncombusted in this particular example. The next slide shows a particularly, I find this disturbing, even over years. This was a very sheer piece of clothing. If you look in the upper left corner, you can see evidence of a flower pattern that was on this clothing. The next slide shows you, I think, the flower pattern more closely. There you can see a flower that's been sewn into the fabric. And what happened in this case is the light from the fireball was intense enough to be absorbed by the areas that were bright flower-like regions, and they burst into flames or melted. The light filtered through the very sheer white material, but of course, there was a surface below the sheer white material, and we'll see the consequences of that. So I always think of this as it seems to me it's like an expression of evil, because the beautiful flowers are preferentially destroyed.
Right.
It has this symbolic effect, to me at least. If we look at the slide 24, we see the consequences of these effects on human skin below the covering. This unfortunate woman was burnt, had patterns of her clothing burnt into her skin. What happened is she had some kind of patterned material that was close to her skin when the light of the fireball exposed. When the material was exposed to the light of the fireball, it either set the dark areas on fire or burnt them onto her skin. And she had the pattern of her clothing burnt into her skin. She would have, in this particular case, she would have been exposed to a flash of gamma rays and neutrons from the fireball. She would have received a significant dose of radiation, which would have further suppressed her immune system. So she almost certainly died fairly shortly after the nuclear attack because she had severe burns. Her immune system was compromised severely, and she probably died a horrifying death from infection and burns.
Right.
Short.
And all that just goes to show, I mean, the whole purpose why you're going into such detail on this is to show just how horrific and catastrophic one relatively small nuclear weapon would be on people, and why the reason I just put that comment up there by one of our viewers, I guess nightmares for me tonight. Well, I'd rather it be nightmares over what could happen rather than reliving what did happen, which is why we talk about how we should never even touch any kind of an issue that accelerates the risk of nuclear escalation, because we need to keep fresh in our minds.
I agree with you, Dan, completely. The reason I show these, keep in mind that these are selected. I have hundreds of slides, but I've chosen one.
Yeah.
In each case, because what I'm trying to give your audience a sense of is the phenomenology. What causes these horrifying experiences, what we've seen from history. I'm not trying to punish the audience by showing photograph after photograph of horror. This is not the point of this exercise. The point is to explain the phenomena so that people can understand what is actually happening. These are good slides. These videos are also good, but I won't talk about them in this particular discussion. I can in a later discussion if people are interested, because they focus on the shock wave. And the shock wave is not the most horrifying and destructive part of the nuclear explosion. Focusing on the shock wave is a mistake. These other effects are more deadly, 3 or 4 times more deadly in terms of people killed in a nuclear attack. 3 or 4 times more deadly in terms of numbers of people killed. Go ahead.
Yeah, I'll just say I want to, in the time we have left here, I want to shift gears here to something else. You actually sent me an email a week or two back where you had been doing some, you and one of your colleagues have been doing some analysis on the performance of air defense systems. And
against ballistic missiles, yes.
Against ballistic missiles, right? Not nuclear weapons. We shifted gears here, but it's important because it's related to some of the topics you've had a couple of months back or earlier this year when we were talking about how the Israeli Iron Dome and David Sling and some of these other things performed against the Iranian missiles that came in, or maybe how the Ukrainian air defense is working against Russian, et cetera. And something I think triggered this whole discussion, and it really stood out to me because you have talked previously on this show about how the claim in the 1991 Gulf War was that nearly everything was shot down by Patriots, but you said, yeah, that was never true. You talked about it at the time. But then on the 20th of December, the Houthis fired a hypersonic missile or a fast missile, you can talk about what kind, that hit Tel Aviv that was not intercepted. It was a single missile. It wasn't part of a big barrage. It was one that all the Israeli systems were unable to shoot down. What have you discovered about this, and how do you compare what happened 30 years ago?
Well, before we show the video, let me just give you a little background. Keep in mind that that my colleague George Lewis and I, who did this work on Patriot, we were under the most severe attack in the United States for saying that this thing didn't work. I mean, we were essentially pissing on the flag in the views of many people. We were unpatriotic. We were labeled defeatist. We were not trying to, just as in this earlier discussion I just gave, I'm not trying to make false claims. I'm trying to explain to people facts that they should be thinking about. I'm not telling them what to think, but there are facts we know that we need to keep in mind when we're trying to reach conclusions about how to deal with a given military threat that we're all facing. And the missile defense has been falsely claimed to be a way to protect our society from not only the effects of conventional ballistic missile attacks, but more importantly, let me remind people that the claims have been made that we can protect our societies from nuclear attack. I have been out there now for 30 years. I hadn't actually trying to explain to people that these missile defenses will not protect us from nuclear weapons. And part of my main reason I have been doing this is not to say, oh, give up. I'm not saying give up. I'm saying be aware of what your real options are. If you have an option that you believe you have and it doesn't work, you need to understand that in your struggle to find alternative ways to deal with this threat.
Yeah, that's massively important, huge important.
And that is why I have spent so much time in my career talking about the shortfalls, the reasons we cannot expect any help at all from missile defenses in the case of nuclear weapons, because and this has cost us tremendously. It's not only cost us money. What the United States did is we withdrew from the ABM Treaty of 1972 in 2002. That treaty put a cap on the number of nuclear weapons that both sides, and in this case China, were building. Because a reasonable question is to say, well, if the missile defenses don't work, why do you want to limit them? Perfectly reasonable question. Well, the answer is, if you're looking at an adversary who's building missile defenses and they're capable, you're never quite sure what they can come up with. So the simplest way to deal with this is to build more of your own weapons. That's the simplest way. It's very easy to understand politically, which means you can explain yourself to your population. It's hard for me to explain to your population, oh, they're decoys, they're countermeasures, blah, blah, blah. But it's very easy for me to say, well, look, we just built more weapons and this guy has interceptors. Right. So the political forces and the limits of what people quickly understand. I'm not trying to suggest people are not intelligent. I'm suggesting that people have their own lives and they're living their lives and they're not focusing on these things. And the political leadership takes opportunities to manipulate its population. We're seeing this all the time now with the newspapers.
Yeah, unfortunately we are.
And so the combination of political and social forces and the reality that these missile defenses don't work have driven the Chinese to make a vast expansion in their nuclear forces. That's why the Chinese have expanded their nuclear forces.
Right.
Go to these idiotic political scientists who are arguing about how many angels can dance on the head of a pin, and they'll have all kinds of silly arguments. The fact is very simple. I just explained that. It's that easy to understand. It's that simple.
Now, let's look specifically at this 20 December missile here. Why did the Israeli systems and its multi-layered capacities not intercept this one missile?
Well, we let's just see the engagement and let me explain it. We have two engagements on the video. One engagement is from December 2024. A second engagement on the video that follows immediately is from 33 years earlier. You'll note when you see them that they look exactly the same, and I'll describe why they look the same shortly after the video ends. But let's take a look at the video.
Ted, where is that video? Where is that?
Do you have it? I mean, I sent it to you.
Oh, let me look for it while you're talking.
You want me to show it? Can you give
Sure,
me
yeah, go right ahead. Please go right ahead.
Okay.
Yep.
Just now, I don't know. I probably have to hit some kind of share.
Yeah. If you'll see, you know what? If you could just send the link to Gary, he'll throw it right up there. That's probably the easiest way to do.
Oh, send the link. I have it in an email which I sent you.
Okay, just resend that one because he get a bunch. It's hard to figure out exactly which one we're talking about here. I flood his inbox every day, so
yeah, I know. I have a flooded. Let's see if I can find it quickly. Inbox sent.
Yeah, one of the things that while you're looking for that's I find really, I guess almost as important, at least on an operational level as even a strategic one, is that, and we talked about this before, in the event that either Hezbollah or Iran ever decided to hit Israel with a barrage type attack, with a lot of missiles, especially some of these that are more capable. Like obviously, if the Houthis have it, the Iranians have it as well, because it's almost certainly where they got it from. But this just graphically shows that in areas that matter, if an enemy of Israel has the capacity and the will, rather, to use some of these weapons, they can get through. And of course, if it can get through Israel's Iron Dome, then that it can also get through our defense systems. And so it's not a shock that many of the Russian missiles are always getting through the Ukrainian air defense systems as well. And that's you said a minute ago something that I think is really important for not just our audience, but for the leaders in Washington to understand. If you think that our Patriot air defense system is going to be able to defend us from everything, that might lead you to take risky action here that could spawn an attack against you. But if you know that your defense systems are going to be, a sieve at the best and just non-functional at worst, then that may create the reasonable caution to not take certain actions that could spawn an enemy missile attack. So that's one of the reasons why I think it is so important to understand what's real and what's just fiction.
I agree with you completely. And I think this is one of the great dangers of all this lying by people who should know better. All right, I'm just sending you right now. It's got no title on it. Just sending it. It's to Gary.
Yeah, I think I just started to hit the inbox here, so I'm sure he'll be able to find that there in a second. But
so this is one of the great paradoxes about missile defenses. They don't work. That's a technical statement. So I want to be clear. I'm saying technically they don't work in the environments that we're talking about, and I can talk about this ad nauseum. But then you have the social and political dimensions of these defenses. They cause people to react as if they work because people have fears that these things will actually, there you go. Okay, great. So why don't we just play, there it is. This is a full speed version. You'll see the next, it's replayed at 1/3 speed. So you'll be able to see what actually, there it is.
Tel Aviv on the 20th of December.
This is Tel Aviv, 20 December. And you see this bright warhead coming in. It passes the interceptor and it passes 2 interceptors. And then we'll see an explosion on the ground. There's the explosion.
Yeah.
Okay. So we can estimate the height at which the altitudes at which these intercepts occur. but we haven't been able to do it. We haven't had the time, but we will do that. But I'm guessing below 10 kilometers altitude. And now this is from the Gulf War. This is January 1991, 33 years later.
Earlier.
Playing this twice. When you get a chance, you want to listen to the voiceover on this because it's great. And this is it in slow motion, just so people can see. And then there'll be a third version of this with the brightness and contrast turned up so you can see things more clearly. So it depends on your audience. I don't know what your audience can see, but they may not be able to see the warhead moving. But in the next slide, you'll be able to see the warhead moving and the misses. I can see the warhead now, but here's the slide with the brightness turned up. So now you can see the warhead.
Yeah, it goes past it, and then just like the Tel Aviv one.
Yes, just past it. And then we go on. We see evidence for something breaking off this warhead, incidentally. You can see that in this instant. And then we see the second miss. You can see the warhead
behind it
very clearly. And so this shows you exactly the same phenomenon. So 33 years later, we see exactly the same phenomenon, which the ballistic missile defense has to be able to solve. It didn't solve this. This was a simple engagement. This was as clean an engagement as you could expect. Now, I only learned this morning from discussions with my tremendously talented collaborator and friend, George Lewis. He's been looking into this. It turns out that the Israelis launched 2 Arrow interceptors at this incoming warhead. So they launched 4 interceptors at this missile. In other words, 2 arrows, and we believe we'll know better in a few days when we can model things. Almost certainly there were 2 Patriot interceptors, because we can't find any other examples of interceptors in the possession of the Israelis that could work at these low altitudes and hope to engage this incoming warhead. Now, there's several things you can tell from this video of the recent engagement, just to cue your audience if they want to look at it again. And I can make this available to anybody who wants the video. The warhead that came in is a much more modern warhead than the ones we were seeing in the past. Yeah. Notice that you don't see any contrail behind this warhead. The contrails we were seeing in the past were because the warheads were primitive and pieces of material were breaking off the warhead. This is a more sophisticated warhead, which does not disintegrate to any significant extent while it's subjected to the high aerodynamic temperatures and pressures during reentry. And the other factor is that it's very bright. And the reason it's so nice and bright and easy to see against the sky is because it's traveling at twice the speed of the warhead we were looking at from 1991.
Okay.
Because it was launched from Yemen, so that's 1,600 kilometers. So it came in at a speed close to 4 kilometers per second. The warhead we were seeing in 1991 was coming in at a speed of a little over 2 kilometers per second. So, this was a different.
Correct me if I'm wrong, but it's entirely possible that the technology, the intercept technology itself, may indeed have been elevated and moving forward, but so too did the missile attack systems. So it still hasn't been able to keep pace with it. Is that
exactly correct? Exactly correct. But these are the kinds of targets that they will be engaged. If for example, Iran decides that its only way of dealing with Israel, I hope they don't do this, but this is also up to the Israelis as well, I might point out. But if the Iranians decide that the only way they can deal with Israel is through punishment rather than military destruction, then they could decide to launch their long-range missiles at the cities just to do a lot of general damage. And as I showed in one of the earlier briefings we had, where we talked about the accuracy of Iranian missiles, which I estimated to be somewhere between 500 meters and a kilometer, which I think was probably closer to a kilometer than 500 meters. A kilometer accuracy is more than enough to be able to barrage large areas of a big city and do extensive damage. And every one of those missiles is going to get through the defense. Every one of them. So if you want to have 100 1,000-pound bombs land in the interior area of Tel Aviv, see if you can push the Iranians into doing that. I mean, that's one way to state it, if I want to be blunt about it.
Right.
I hope it doesn't happen.
Certainly do as well. I'm sorry, we're running low on time here,
Yes.
but I don't want to let you go without getting an update on the Oreshnik missile, because one of the things that you pointed out to me before we even went on the air here today was that even though the speed of the Oreshnik may be similar to, because you just estimated that last one was going about 4 kilometers a second, which is something close to the Oreshnik, except that this one has got the multiple warheads, which makes it nearly impossible.
Absolutely. And the Oreshnik missile looks like the, this is another discussion, so I'll be brief on this. I've looked into the possibility that it had explosive material on the warhead. I think it makes sense. I believe the explosive material is a mix of tiny aluminum particles, like the tiny aluminum particles used in rocket fuel, because they make the people who launched the Oreshnik have solid propellant rocket fuel, so they know they have this tiny aluminum that's used, tiny particles of aluminum. You mix the tiny particles of aluminum together with ammonium perchlorate, because you need an oxidizer, so you have an explosive effect, because you need to oxidize the aluminum very quickly. Aluminum, when it ignites rapidly in an explosive, has about 10 times the release of energy per unit weight as TNT. So you can get a very large energy output from the aluminum. The density of aluminum and ammonium perchlorate is low. So if you mix particles of tungsten in with it, you can make the average density high, so you can get a high ballistic coefficient in the warhead. You don't need to alloy it like some people are talking about. You don't need an alloy. You just need a powder mix. Load it, mix it, load it into the center of the warhead with a shell around it. When it hits the ground, the kinetic energy will create a high temperature environment just from converting the motion, the kinetic motion of the warhead into kinetic energy. The kinetic energy will create an environment of extremely high temperature, which will then cause the explosive release of the aluminum combusting with the ammonium perchlorate, and bang, you have an explosive event. My very rough initial calculations is you probably have, in effect, an explosive event that's about 3 times the weight, its equivalent weight in TNT. So if it's 100 kilogram munition, it maybe has the explosive power of 300 kilograms of explosive, maybe. I'll have more detail on this later.
Okay, and the Putin in a speech, I think it was the day after Christmas, said that, hey, we don't have a lot of these. We have some, but we're building more. So would this be the kind of situation for it to be really militarily effective, that it would have to be fired in barrages and not like a single missile, because of this, the error probability that you talked about there, to hitting any pinpoint targets?
Well, the Russian precision delivery is much better, of course, because they have more, their guidance technology is far improved. I can only guess what the accuracy of the Russian system, the Oreshnik, was. I'm guessing it's about 100 to 200 meter accuracy, not a kilometer, But 100 to 200 meters, I mean the center of the
Yeah.
collection of munitions. What we did not see are the munitions collected together very closely. And there's no reason why the munitions couldn't be dispersed in a very tight pattern, because they were shooting at a large area target, so they probably dispersed the munitions intentionally.
Oh, I see.
So
it doesn't necessarily have to be spread out. They may
right,
set up settings to
exactly.
make it.
So
didn't know that
so
either.
you could have
Been very useful.
5 or 6 of these munitions landing within a circle of maybe diameter of radius 200 meters, say. Well, that's not a lot, but if you have 2 or 3 Oreshnik missiles coming into an area of maybe 200 meters radius,
Yeah, that's
with
going to cause a lot of
36
damage.
bombs of maybe 300 kilogram explosive bombs, 500-600 pounds, 500-pound bombs, it'll get your attention.
Yeah.
Right.
So, all right. Well, listen, we really appreciate this update today, and as you get more information, we'd love to have you come back
certainly,
on and let that up.
The problem is you can generate questions much more quickly than I can analyze them.
Well, I know, but you almost always have answers. That's why. So you've already educated me more than I was before the show. So I'm, as usual, I'm appreciative of that.
Well,
and I know
we'll stay at it. We'll stay out of it.
All right. Well, listen, thank you very much. And I hope you have a wonderful new year. If I don't see you before then,
you too.
And we'll look forward to catching you early in 2025.
And remember, Gary, you take your shoes off when we get up to those numbers above 10.
I will. I got you.
Okay. Thanks a lot.
All right.
Bye-bye.
Well, listen, and I appreciate you guys also. Remember that we are on podcast now. I know a lot of you don't have time to watch all the shows, but you do have time to listen to them. Apple Podcasts, Spotify, Podcast Addict, wherever you go, type in Daniel Davis Deep Dive. You'll find our podcast waiting there for you. And in the meantime, in case we don't see you guys also, we wish you a happy new year. Thankful very much for your viewership over this past year of 2024. It's been a fantastic one for us, in large part because of what you guys have been doing and coming on and watching us and sharing it with your friends. And we really do appreciate that. I want you to know we never take that for granted. And we'll continue to give you shows. We got some more stuff tomorrow. So it's not like we'll signing off to see you until 25. We'll be back tomorrow. So we'll see you on the next episode then of Daniel Davis Deep Dive.